it's my distinct pleasure to introduce this afternoon's colloquium speaker, which is none other than our own Professor Lisa Cooley. As we all know, Lisa was appointed the CFA director in July of this year, so 3 months ago. And I think as you've already seen in those intervening 3 months, she's embarked on a very ambitious program to set us a vision for the CFA for the next decade and beyond, focusing on space-based and or next generation space-based and ground-based telescopes, data science and handling of petabyte data sets, initiatives related to diversity and inclusion, and a nationwide program of outreach and education. Some of us may be less familiar with her research, which is focused on star and galaxy formation, which is incredibly impressive, has received worldwide attention, and which she's received a number of accolades. So, not to embarrass you, but I'll just quickly run down your CV here. So Lisa obtained her PhD from Australian National University in 2002, working on the connection between star formation and supermassive black holes and galaxies. She then came to the CFA as a CFA fellow, and then continued on in Hawaii as a NASA fellow, ultimately returning to Australia. She's won many, many significant awards. Just quickly, she won the Annie Jump Cannon Award from the American Astronomical Society. That was followed several years later by the Newton Lacey Pierce Prize. She was elected a fellow of the Australian Academy of Sciences. She was also awarded the ARC Laureate Fellowship, which is Australia's top fellowship to support excellence in research. That was followed by her being awarded the James Clark Watson Medal in the U.S. National Academy of Sciences, and then quickly elected into the National Academy and the American Academy. And for the last 5 years prior to her coming to the CFA, she is then implementing her scientific vision through the Australian Research Center, Council Center for Excellence, the All-Sky Astrophysics and Beauty, which is a multi-institution and several hundred participants. So we're delighted to have Lisa here talking about her research, and her title is Next Generation Photoionization Modeling.
Okay, thanks, Mike. Can we get the lights turned down? Perfect. Okay, so it's wonderful to be here talking about science, and as Mike said, this is something that you may not have heard so much about, and it's something that I don't do so much of these days. So a lot of the work I'm going to show you is work that's being done by postdocs and students that I've been privileged to work with, and you'll be seeing their names and photos on various slides when their work is shown. Okay, so I'm just going to give an overview of the talk here. So I'm going to give a quick overview on our theoretical modelling and advantages, and I'll talk about advantages and disadvantages of the models and the different techniques that we're using, and then I'm going to describe what we're doing towards fully self-consistent photoionization modelling, and this is for H2 regions, but it's also for galaxies. And then finally I'll talk about what we're aiming towards, and in particular the next generation telescopes and being able to analyse data from those next generation telescopes. And so this is a diagram of what we currently do in order to produce a theoretical spectrum to analyse a star-forming region or a galaxy. And in particular, we have to use a stellar atmosphere model and stellar tracks, and they go into a stellar evolution synthesis model. That produces a theoretical ionizing radiation field, which then goes into the photoionization model, which is basically it models the gas surrounding the a cluster of stars. And these photoionization models track the ionizing radiation at each step through a nebula and calculate the detailed emission from the various lines, and it includes a whole bunch of emission line processes, including collisional excitation, recombination, and so on. And we include in our models a dust model, and then the model output is a theoretical spectrum, and the theoretical spectrum covers the X-rays right through to the submillimeter, and so we actually have a very detailed emission line spectrum that's produced by these models and can then be tested against observations. Now, it's not as simple as that because there are a lot of inputs into the models, and so for example for the stellar evolution synthesis model we have to input an initial mass function, we have to input the stellar population ages, the history of the star formation, metallicity, And we also, in the photoionization model, we then have to input other parameters, including an ionization parameter, which tells you the amount of ionizing radiation that's produced by the star cluster. This is actually related to the star formation rate as well as the age of the population. And we also need to put in an ISM pressure or density related to the temperature, and metallicity and a geometry. So there's a large number of assumptions that go into these types of models. And so I'm going to focus first on the top section of the models and what we've been doing in recent years in order to improve our predictions. And so we have to get an ionizing radiation field, and this is an ionizing radiation field that we get from stellar evolution synthesis models. We usually use Starburst 99, and what we're interested in particularly here is this part of the spectrum. So this is the spectrum that's producing the emission lines that we observe in the UV or the optical and the infrared part of the spectrum. And they're critically sensitive to the ionization potentials of the elements, which are shown here. So the red begins the ionization potential of for example, this one's H1, and orange is the second ionization potential, and yellow is the third ionization potential. And the problem with this is that they're very, very sensitive. So the emission lines are very, very sensitive to where the ionization potentials are, and then how much the spectra change as a function of these other parameters that I just described. So for example, these models here change critically depending on the age of the stellar population. And so we need to know stellar population age ideally to constrain these models. They also depend critically on the metallicity of the stellar population. So you can see here that the different metallicities, which are the different colors, really strongly change the shape of the ionizing radiation field. So if we don't have that, then it's actually hard for us to produce the accurate emission lines. And then it's also hard to produce the accurate emission lines if the stellar atmosphere models are not producing the ionizing spectrum that we're expecting. And so in particular, to model low metallicity galaxies or low metallicity H2 regions, it turns out that we need to have a soft X-ray excess in the ionizing radiation field in order just to reproduce the optical emission lines that we see from nearby H2 regions. And so this means that we actually, the stellar atmospheres are it's very complicated to model, and this is what we consider at the moment is to be the real bugaboo of the models, and this is something that is an ongoing issue with the models, is producing accurate stellar atmospheres in order to reproduce our observations. And so this is an outstanding problem. Now another question is the stellar tracks. And so we're using stellar tracks, which are based on large libraries and our understanding of stellar evolution inside stellar evolution synthesis models to produce the ionizing radiation field from a stellar population. And I often get asked whether the stellar tracks have an impact on our emission line diagnostics. And these are diagrams that we use to determine whether a galaxy is star forming, which would mean it lies in this part of these diagrams, or whether it's AGN, it would lie in the top part of the diagram if it's an AGN. And so if we change the stellar tracks, they don't have very much impact on the optical emission lines, fortunately. And similarly with using stochastic versus non-stochastic IMFs. But the abundance sets that we input into the models make a very large difference. And in the past, over the last 3 decades, we've been using these abundance sets from Anders and Graves, which are the most common abundance sets. So when I talk about abundance sets, I mean the amount of an element relative to hydrogen. And so we have to estimate what they are for 30 elements in the models, and this is an input into the model. And so the problem is that when we actually look at data, and so this is data from nearby stars and H2 regions, when we look at that data, you can see that the stellar ratio, which is shown as a dashed line here, may be right for something like argon to oxygen, but it doesn't appear to be correct for neon to oxygen. So it actually changes with metallicities. And what we've been doing is we've been using solar and just scaling it up and scaling it down for all the elements except for carbon and nitrogen, because they have a primary and a secondary nucleosynthetic origin. And similarly, if you look at chlorine to oxygen and you look at the data, then there's actually, you know, the Anderson-Graves is here, it's clearly not right, and so you'd want to be using something like this, or perhaps something more in the middle. And so what David Nichols did, who's a mature age postdoc at the ANU, is that he took these observations, so as many stars and nearby H2 regions as we can measure, and derive new abundance sets, and they're scaling with metallicity. And he calls this the galactic concordance abundance sets. They're based on galactic H2 regions and nearby stars. And this shows you a comparison of the major impact it has in our ability to predict emission lines. So this is the oxygen 3 line that's in the blue, divided by H beta, and this is the nitrogen 2 line in the red, divided by oxygen 2, which is in the blue. And this diagram is commonly used, I mentioned earlier, to separate star-forming galaxies which lie here from AGN galaxies which lie here. And this is Sloan galaxies. And you can see that the previous abundance sets, which were uniform scaling with solar abundances, are shown in black. And you can see that they're not reproducing the full range of emission line ratios that we see in the star-forming galaxies, whereas the red ones, which are our galactic concordance non-uniform ones, do. And so they're able to reproduce very well the full range of emission line ratios seen in the Sloan galaxies. And it doesn't matter which type of abundance set scaled with solar you use, they all have this sort of crunched up kind of shape on these diagrams, whereas if you do non-uniform scaling, you're able to reproduce it more accurately. So this is now what we're using. The problem was that we were introducing the galactic concordance abundance sets in our photoionization models, but they were not the same in the stellar evolution synthesis models. So to produce stellar evolution synthesizing radiation fielding, making that consistent with the photoionization models of the surrounding gas, we actually need to introduce stellar tracks which have the galactic concordance abundance sets in them. And this is hard work. And this is work that's been done by Katie Grasher. She's a postdoc at the ANU and a discovery early career researcher. And she's actually going to be visiting in a couple of weeks for a few weeks. So if you want to talk with her about that, come and see me. So she derived new stellar tracks. She used MESA, and this was a collaboration with Charlie Conroy's group, and fit the galactic concordance abundances for hot, massive main sequence stars. They're what we're interested in when we're comparing with H2 regions and star-forming galaxies. And so with these new stellar tracks, we can then have a look at the impact on the ionizing spectrum. And so this is the ionizing spectrum here. This is the amount of ionizing photons versus age. And the most important thing is to compare the pink ones, which are the Stromlo Stellar Tracks, with the galactic concordance abundance sets, with the regular solar ones, which are in black. And you can see the difference gets much larger as you go down in metallicity. And this is something we're always seeing. We're having a really hard time modelling the low metallicity star-forming regions, low metallicity galaxies, and there's a big difference here between the ionizing photons when you go down in metallicity, depending on which abundance sets you used and scaling. And so what Katie is now doing is she's now looking at creating stellar tracks for higher redshift galaxies, and in particular using chemical abundance simulations by Chiaki Kobayashi and group in order to predict how the various abundance ratios would change with redshift, and then to be able to produce redshift dependent stellar tracks. And she's also had a look at the relationship between the local ionization parameter and the metallicity. This is really hard to model before. In fact, the models usually produced a line that went in the opposite direction. Now the models are able to reproduce the data which are shown in dots, and there's a strong relationship between the ionization parameter and the metallicity, and we think this is associated with the impact of metallicity on the stellar atmospheres and their ability to then produce the ionizing radiation field. And so when we look at, now this is what we had before, I showed you before the ionizing radiation radiation field with the previous stellar tracks. Now, if we zoom in on this important part of the spectrum, we now have these various ionizing radiation fields for the different stellar tracks, and we can do it as a function of age and metallicity. Okay, so that's that part of the model. And now I'm going to move to talk about our advances in the photoionization part of the model. And so we have a stellar evolution model which produces the ionizing radiation field. We then put it inside the gas, and we're trying to model a gas nebula. And this is very complicated, and there's a lot of improvements that can be made in this area. So firstly, we have to deplete the elements out of gas phase onto dust grains. And the question is, how do we do that? And it's been really hard to actually estimate accurately the depletion for 30 elements. Some elements aren't depleted, so it's not quite 30. But how do we actually do that? And so one way of doing that we've been doing is to go out to the Siding Spring Telescope. This is in Coonabarabran in Australia, and use the wide field spectrograph to image H2 regions, imaging spectroscopy. So we're getting spectroscopy at spaxels all the way across single star H2 regions of different metallicities. And we're doing a thing called hyperspectral imaging observations, very, very, very high signal to noise observations, so that we can actually use our models to back out the dust depletion factors. This is Mike Doppiter. He was the one who built WIVES, the spectrograph that we're using. And so then I just want to stop briefly and say that in Australia, going out to Siding Springs is extreme astronomy. We have redback spiders here, which don't usually kill adults but can kill children. We also have things like red-bellied black snakes. In fact, they sometimes come into the observatory in Canberra too. We have eastern brown snakes, which my son saw this last night and said, I stepped on one of those back when we were in Australia, and it luckily slithered away, and I didn't tell you because I don't want to worry you. So we also have things called drop bears, which are very, very vicious koalas that fall on you out of trees, territorial. We do have bushfires that come through. In fact, this telescope has seen 2 bushfires and survived. And we have very dangerous animals called kangaroos as well. And so after these observations, we were able to get this type of spectrum, which every single wiggle in the spectrum that you see here is actually an emission line. And so you can zoom in. This is really beautiful. And every single thing in here is an element. And so when you get to this much detail on individual spaxels across an H2 region, then you can actually use the models, and you know what the star is because it's a single star, and so then you can actually turn the models backwards and solve for the dust depletion factors. You're trying to solve for 30 things, and so this is the way to do it. And this is ongoing work that David Nichols is doing at the moment. And so this is something that we're hoping to include in the models in the next couple of years. When you go into that much detail, you actually need to understand the physics very well in those H2 regions as well. And so these are the different options right now for photoionization models. We have mappings, which is the model that we're using. And then we have cloudy, which is basically the competing model, which also does photoionization models. And these do very, very detailed photoionization emission line processes of about 30 elements, each of them. They're very similar. And then we have a different type of photoionization models, which are ray tracing Monte Carlo models. And so these ones here, they are less detailed just due to computational requirements. They're less detailed. But however, they follow lines of sight of the ionizing photons through the gas, and you're able to get much more accurate geometries from these types of models. So we're aiming to sort of merge these 2 types of models together. But first, I'm just comparing cloudy and mapping. So lots of people ask, how do they compare? Very well. They basically produce very, very similar results on these optical diagnostic diagrams, as long as you put in the same input parameters. But one problem with previous, interpretations or previous usages of these models, of these types of models, has been that H2 regions are generally been assumed to have constant density and temperature. And this is an example. So if you use Osterbrock, which is basically like the Bible for AGN or for H2 regions, it's the book every student has to read. Osterbrock tells you that you need to use these curves to estimate the densities from the sulfur 2 emission lines or the oxygen 2 emission lines, and these assume a constant temperature across the H2 region. And similarly, if you want to use the auroral lines, which are these particular lines, particular transitions which are produced in aurora on Earth, and if you want to use them to get an electron temperature, they're very sensitive to the temperature of the gas, you have to assume a constant density across the H2 regions. Now that would be okay if they were constant, however they're not. And so with our hyperspectral resolution data, we're able to do Orion as well. And this is an example of Orion, where you can see the electron temperature and the distance from the central ionizing source for this part of Orion. And these are two different, the red and the black are two different ways of measuring the electron temperature. And you can see it's very definitely not constant. And the electron density is the same. As a function of distance, it's very definitely not constant. And in fact, it goes down with distance. And we know that when we actually look at H2 regions, and these are maps that were done by Yufei using the Wive spectrograph, there you can see the temperatures and the densities. They're, very, they've got a lot of structure in them across the nebula. So this is the electron temperature in oxygen 2, nitrogen 2, oxygen 3, and these are two different ways of measuring electron density. And, they're really not constant. In fact, all the ones we looked at actually aren't constant. And so what we need to do is actually to include a changing electron temperature and density through the nebula. So with our most recent models, this is what we do. So we assume a constant pressure because the pressure in an H2 region is typically determined by, an H2 region would expand until it reaches some sort of equilibrium with the surrounding gas. It may be confined if it's in a dense region, or it may be able to move out further if it's in a less dense region. And so here, these models show with a constant pressure nebula what you would get for the electron temperature and the electron density as a function of distance. And you can see that they're mostly not constant with distance. And in fact, there's only a few metallicities where you might consider them to be constant. And so the question is this enough? Is this enough to produce an accurate model or not? And the answer is probably no. So this is a very complicated figure. This is made by my student Yufei Jin, who's actually coming here as a postdoc in a couple of months. And this shows electron temperature and density versus thickness. And you can see these are the observations in the green and the blue and the red. And so the observations really are changing quite a lot. And so the conclusion is that the models with just a constant temperature or even a changing temperature or density are not sufficient to reproduce the observations. And these are observations at different metallicities. So these are H2 regions in the LMC and the SMC. Okay, so now we need more accurate nebular structure. The models are not good enough for these type of observations of H2 regions. And so when Yufei observed the temperatures across these different H2 regions and in the different emission lines, he saw quite a lot of structure. And we needed to really get a handle on how we're going to model this more accurately. And so the advantages of the current models that we've been using is we can do 30 elements. They're very detailed. They can predict quite well the emission lines in the X-ray and the UV and the optical and the infrared and submillimeter for galaxies. And for H2 regions in general, when you're looking at it a whole sample. But when you're trying to model individual objects, then it becomes harder. And they now do take temperature, ionization, and pressure structure into account, but the problem is they're limited to spherical or plane parallel geometry. And so we're always assuming that the H2 regions are a spherical cow. And we know that H2 regions are not spherical, and so they can be bipolar, like this. They can be blister-like, and so they can actually be butted up right against each other and they can form blisters, so you can have an additional H2 region formed right alongside another H2 region and not spherical. And they can have concentric shells and all sorts of other things, and which make them not spherical. And so we wanted to see if we could produce Monte Carlo ray tracing photoionization models. And so this is the PhD topic of Yifei, and so what he did was he created 3D Monte Carlo radiative transfer. He used the method in Grzynia Stasinska and Ercolano's paper, modified so that it can be run using 30 elements and through the very complicated nebular structures that we want to use here that are really, we think, more realistic compared to observations. And so these are snapshots or slices through this nebula in different emission lines. And so you can see that we are seeing ring type structures and you know, various types of geometry in these models. This is a map of the oxygen 3 is in red and H beta is in dark blue and cyan is nitrogen 2. And so you can see that we are able to reproduce roughly. The resolution's lower than we get in real observations at the moment, but we are able to get a more realistic geometry than certainly assuming some sphere. And so this is important because it means that with these type of models we can begin to understand the impact on the predicted emission lines for all the modelling that we've done in the past. And so this is an example of a nebula that we produced. This is a fractal type geometry, and we now compare the 3D emission line fluxes with the 1D emission line fluxes. And so that's this figure here. And I should note that how much emission lines are produced depend on their distance from the ionizing source, and that's very straightforward in a sphere. But when you've got a complex nebula like this, it actually depends on how many lines of sight have a certain distance away from the ionizing source. And in particular, edge effects, where emission lines that are produced towards the edge of a nebula, which are typically sulfur 2 and oxygen 1, and a little bit nitrogen 2 as well, actually have the main impact from these types of models, okay, because there are a lot of edges that are produced in this type of fractal nebula. And because there are a lot of edges, then what we get is that lines like sulfur 2 and oxygen 1 have the largest difference between the 3D and the 1D models. And in fact, it's a factor more than 2 in the oxygen 1 line. It was very hard for us to model oxygen 1 always in the past. And small impact on nitrogen 2 and oxygen 3, and no impact on the Balmer lines. And so now what we're doing is producing different types of H2 regions, and then we can compare them directly with each other. So this is the spherical, this is the on the left-hand side is the fractal geometry, and you can see the different emission lines that we use, and these are typical lines for diagnosing properties of galaxies. Nitrogen 2 and H alpha is used as a metallicity diagnostic. O3H beta is the primary distinguisher between AGN and star-forming regions. R23 is a metallicity diagnostic, and this oxygen 3 and oxygen 2 is an ionization parameter diagnostic. And you can see for all of these different diagnostic lines, there's a vast difference between what you would get for a spherical model and what you would get for the fractal geometry model. And so there's major impacts on our ability to estimate all of these properties, metallicity, ionization parameter, how much AGN's in a galaxy for these type of models. Now, importantly, because we have the Balmer lines are unaffected, but some of these other lines are, like nitrogen 2 and sulfur 2, then this impacts our ability to classify galaxies. So that's where the work currently stands at the moment. Yifei is currently now analysing the impact going forwards on the diagnostics, and so what we want to do now is to produce new metallicity and ionization parameter diagnostics for star-forming regions with different types of geometry. And so if you have an H2 region that's a blister H2 region or a bipolar H2 region, you'll have the right models to compare with rather than assuming everything's spherical. And so this is what it now looks like for deriving our next generation photoionization models, and we're up to this stage now. So we took the SMC and LMC and Milky Way H2 regions and then introduced a fractal geometry and the new dust depletion factors that David's been working on. And then Katie also worked on the galactic concordance. David and Katie worked on galactic concordance abundances, and Katie derived the new stellar tracks with the stellar atmosphere and stellar evolution synthesis models. And now they're going into the new updated 2D and 3D photoionization models. And so I'm just going to show you a couple of why we're doing this work. What are we aiming towards? So we really need to be able to model JWST data, and we need to do it in a way that we believe is more reliable or robust than we did in the past. And so with JWST, the core galaxy evolution science is moving out in redshift, right? So you people that were working on what we called high redshift in the past was redshift of 3. High redshift is now redshift of 9. And so what we're trying to do now is with JWST data, we're able to get star formation history and chemical history for galaxies across a much larger redshift range. And so to do that, we actually need to have reliable metallicity diagnostics, ionization parameter diagnostics, star formation rate diagnostics. And so that's what we're currently deriving. This is a Z of 14 candidate galaxy with model fits from a paper. I'm involved in the SEERS early release science program that's being led by Stephen Finkelstein. This is our mapping prediction of a Z of 9 star-forming galaxy with these emission lines. And so typically the emission lines we get is oxygen 3NH beta, sometimes O2, and possibly UV lines. Okay, so what's next? So what we want to do now is, as I said, derive new self-consistent diagnostics for H2 regions of star-forming galaxies, and we're also at the same time working on AGN and shock diagnostics, because an advantage of mappings is that it does shock models as well as AGN. And in the past, we threw out AGN and shocked galaxies from our studies of the star formation history and the chemical history of the universe, and we don't want to throw them out, we want to include them. And to do that, we actually need to be using the correct models. We need to be using AGN models and models of shocked regions if we know that a galaxy is dominated by those things. And then finally, we want to derive the co-moving star formation metallicity history of galaxies between redshift of 9. Now, this is a sneak preview of Peixin Xu's work. Peixin's here. She's become a PhD student here at Harvard. And this is work she's been doing in Australia, and which she's continuing here. And she's been working on metallicity diagnostics using the new models, galactic concordance abundances, in the optical UV as well as infrared bands. And previously, we didn't have very reliable metallicity diagnostics using AGN models. And Peixin was able to resolve some ongoing discrepancies between different AGN diagnostics, and these are now really beautiful. She's currently preparing this for publication, and so these are diagnostics for metallicity using the line ratios nitrogen 2H alpha, nitrogen 2 and oxygen 2 for AGN, and there's quite a lot of good metallicity diagnostics that we'll be able to use for AGN galaxies. These are some other diagnostics in the infrared band. And also we're looking now at dust attenuation and how do we derive dust attenuation curves because they may change with metallicity. And so this is work that's being done by Andrew Badisti, who's also visiting in a couple of weeks. And Andrew's been using a survey called Typhoon, which is a survey of 44 galaxies where this is led by Barry Madore at Carnegie. And what Barry and his team did was they stepped a slit across these massive nearby spiral galaxies to create the largest IFU data cube for the largest data set that we have. And this is very beautiful data. So just to show you the power of this is a galaxy where we can get a data cube of. This is the Sami footprint, Manga, Muse, and Calipha. You can't get an entire nearby galaxy. We need resolution at the scale of the H2 regions. You can't do that with current instruments. You have to do this stepwise long slit approach. But this now gives us 44 galaxies with data cubes where we can actually derive things like dust attenuation factors also because of the large wavelength coverage on these very large famous galaxies. And so this is, he's derived this one here from NGC 3521, attenuation curve. And this attenuation curve agrees pretty well with the local, this is a local galaxy, it agrees pretty well with the other attenuation curves of other local galaxies. And now he's applying it to galaxies, the same technique to galaxies in the Typhoon survey with different metallicities and different stellar masses and different star formation rates to derive prescriptions for all these different types of galaxies. And this has been really difficult to do in the past. It was really only possible in the Milky Way and nearby galaxies. And that's been, this is really revolutionizing our ability to do these curves. And then I'm very excited by a couple of future instruments. Of course, the GMT. Now, GMAX, which is an instrument that we're building here, it's aiming to get spectra of galaxies at the epoch of reionization and also resolve galaxies, but really it's workhorse spectroscopy. And so this is going to be fantastic for understanding these galaxy evolution properties and applying these models to. So James Webb Space Telescope will give us some emission lines, but what we need, we need more elements. And to do that, we're going to need to combine something like James Webb or future near-infrared or infrared spectrographs with ground-based spectroscopy as well, because we need a broader wavelength coverage of the most distant galaxies. And then also another exciting instrument is GMTIFS, which is being built by the ANU for the GMT. And this is our simulation of star-forming regions of one of those spiral galaxies in Typhoon. This is NGC 628. And this is the type of star formation map we're getting in our data cubes using Typhoon nearby at the moment. But with GMTIFS, we'll be able to do it at redshift of 1.5. So that means attenuation curves, metallicity gradients, and really detailed understanding of the star formation physics and dust that's at redshift of 1.5, which would be really fantastic. And then finally, I think I'm even more excited by Athena X, and I really wish it hadn't been delayed as much as it has been, because Athena X is like if someone does chemical evolution, you're just going to have to love Athena X. There's no denying it, because it's going to be amazing for measuring these various different chemical elements in galaxies, and including as a function of redshift. And I think this is going to be great for looking at the chemical history of clusters in all these elements. And I think we're getting ready to be able to do this theoretically, and it'll be great to have the observations available. So that's something that I'm very excited by. And yeah, and I think I'll conclude there and just say that the next generation of photoionization models is coming. Thank you.
Thank you very much, Lisa, for a great talk. We have time for questions.
The fractal model, the difference between the volume and the surface effects for those different lines, it looked to me like you could then use that to define the fractal dimension of a cloud. Have you looked into that, and is it possible?
Yeah, so we're running a large grid at the moment. Takes a long time to run one of these models. And Yafei's coming here, as I said, as a postdoc, and we're hoping that the Harvard cluster will be much better for running these models. Once we have a large grid, that is one of the plans, is to be able to basically characterize the geometry with a couple of parameters, and then to be able to use that to be able to derive those for H2 regions. So it's like playing the models a bit backwards.
Lisa, beautiful talk. How do you deal with the depth dimension in all of this work? For example, in Orion that you started with, can you use Gaia to give you distances to the ionization sources? Does that enter into the model? Because you're always looking at a projected.
So we haven't tried that. The models that we've done so far, we're trying to use simple H2 regions because, we don't want to, because we're trying to back out other parameters like all those dust depletion factors, we actually wanted to we're using a single star H2 region for those studies because we need to know very well what that star is, so it's not a parameter. And so in distance, we actually know the distance from the star to the gas because we have those observations. And so we need to constrain those parameters very accurately. With Orion was just something we did because we like Orion, and Orion's really fun. And it's very complicated, and different parts of Orion actually can tell you different things about the physics of the ionized gas and how lines are being produced. And there were some fun papers that came out of it. We haven't actually specifically looked at depth in Orion yet. Part of it is that Orion's such a complicated nebula to model, even just in this direction, that I think it would be really hard to try to get a model that accurately does Orion. Yeah.
We have an online question.
Yeah, a question from the chat from Steve Wilner. Do the 3D effects matter very much for infrared lines, such as neon 212.8 or neon 315.5 microns?
I can't remember off the top of my head. We've been focusing on optical so far, but I can certainly get that information from the outputs. Yeah. So if he's interested, I can get in touch.
So Lisa, you mentioned that the data indicate density declining as you go away from the star.
Mm-hmm. In this particular
That particular guy. But is that an indication of a wind? Is that what's going on, or why should there be a gradient?
Yeah, it can be. There's a lot of, it could be a wind. And if there's a wind, you're going to expect the H2 region to have expanded to the point where, you've got some equilibrium with the surrounding gas in pressure. So that's one situation, but we don't see that everywhere. So we're often seeing quite a much more complicated density structure when we looked at the other H2 regions. So that was just in that particular part of Orion that we were looking at. So I wouldn't take that as like everywhere. It's much more complicated than that.
But in general, do you model the velocity structure as well, or is it only density and temperature?
It's just density and temperature, but UFA is actually just now including a dynamical evolution code called FIRES, which actually models winds from stars. So he's put that inside the mappings 5 Monte Carlo models to see what happens, and the models are running at the moment. So I expect when he comes here, he's coming here for 3 years. So when he comes, ask him to give a talk on that because he's running them at the moment. But it's super exciting. That's totally the way to go for those models. Yeah.
Secretary.
So, as you know, galaxies are made of lots of H2 regions.
Yes.
So does that make the problem easier or harder? Because you can imagine it's easier because you get some central limit theorem-like behavior, or harder because you've got many different morphologies that don't behave that way and they get more complex.
Yeah, we've tried to get to the answer to that by looking at galaxies where we have global spectra, where it's been drift scanned across because the current IFUs don't cover all of the galaxies. But there's old data which were drift scanned, and some of the Typhoon galaxies actually have the slit covering the whole extent of the galaxy. And then looking at the individual H2 regions and seeing if we take the average of the emission lines for those H2 regions, do we get the same as the drift scan? And you do. It's remarkable, and this is also work that had been shown years and years ago by Chip Kobylnicki, and we just basically confirmed it. So that implies that it should be that it's more simple to do a whole galaxy because they're kind of averaging out. When you're looking at a single galaxy, though, it's clearly very complicated, and if we were able to go into as much detail in a nearby galaxy as we can in our own Milky Way in the H2 regions, we'd find there are all sorts of shapes and everything. But I think the answer is that we're lucky that it turns out that it's kind of averaged out.
Another online question.
Question on the chat from Roseanne de Stefano. Do the MESA models used include binaries? If so, do they make a significant contribution?
So we didn't include binaries in those models. That is something that Katie Grush is looking at the moment to do some binary modelling. That's a collaboration with Eldritch and collaborators in New Zealand.
So in earlier part of the talk, you've shown us how the non-stellar scale stellar drive back the optical emission diagnostics. Could you tell us a little bit about like how they affect the red frame UV emission diagnostics?
Yes, so there's actually a strong impact on the rest frame UV lines, some of them. It's the lines that you'd probably expect, so it's like carbon-2, so it's a lower ionization species. So there's carbon-2, there's an oxygen-2 line there in the UV as well. The high ionization species like carbon-3 is a little bit affected, not much carbon-4, things like that.
I have like a more general question. The results you've shown, they're really beautiful. But the question is, how can you reach beyond the community doing photoionization with your results? That's why I'm asking this is because a couple of weeks ago I was at a conference on AGN and dwarf galaxies.
Mm-hmm.
And I saw a lot of, well, how to put it politically correct, unsubstantiated claims and unjustified assumptions. Like, people would look at the BPT, they say, okay, maybe the dwarf AGN will be in the star-forming sequence. But if you look at the O1 line, if it's off, then it's definitely an AGN, not a star-forming galaxy. And I saw the answer in your talk that it's not true because of the geometry.
Yes.
So the question is how to reach to people, how to provide them with something simple like a BPT diagram saying that, okay, this is an AGN or this is a shock, this is...
Yeah, years and years ago I was going to write a paper on how to identify low metallicity AGN on the BPT diagrams. There's a lot of degeneracy for AGN on the BPT diagrams. Metallicity does move it towards a star-forming sequence, and they can be on the star-forming sequence, but then if you have complex geometries. So these models were not for AGN. They're for star-forming regions. But for AG, we'd have to have the full, dynamical 3D hydrodynamical models of AGN and then put that. That's much more complicated. But you can get a dwarf galaxy that has an increase in its O1 just because it's dominated by 1 or 2 H2 regions. It's probably worse for dwarf galaxies because the light is usually dominated by 1 or 2 or 3 H2 regions, and then you're dependent on the geometry of those H2 regions. So yeah, it's quite likely. Yefei's doing a paper on the BPT diagrams at the moment. Yeah.
Question in the back. Chef.
So earlier in the talk, you mentioned that you need I think you said a soft X-ray excess in order to explain some of the spectrum. So is that coming from the star itself, or is it a deficiency from the background?
We think it's turbulence related possibly, but really unclear. We don't really know. We've looked at trying to put in the soft X-ray excess to be able to match the emission lines, and then just put it out there and say this is what we need. And
There's
come up with
no
some
idea
models,
where that
but
comes from? There's no idea where that comes from?
no.
Thank you for giving this talk. And this is not my expertise at all, so there is asking a very basic question. But all the way at the beginning, you mentioned that changing the evolutionary tracks doesn't really change. I think you said if you infer if it's star forming or an AGN galaxy. And I have two questions. I'm kind of surprised. Why? And second, you make this. I guess there's a general distinction between star-forming or AGN galaxies, but how clear is this distinction? Because I can assume that there must be some star-forming going on in galaxies with AGNs as well.
Yeah, so those diagrams, you've got a star-forming sequence, and so if you've got pure star-forming galaxies, so galaxies which there's no evidence in any wavelength of AGN, they lie, and H2 regions lie along this one sequence. And then you don't need much AGN to bring it off that sequence. So a 20% AGN is enough, or even 10% is enough to bring it up off that sequence and pop it into the AGN part of the diagram. But if you've got dust, it could bring it back down again. And so very dusty star-forming galaxies are likely lower on that diagram than a AGN that's less dusty. But the diagrams have actually been, they're pretty well used and they're well tested. They're tested with VLBI, with X-ray, hard X-ray emission, you name it. Almost all of the time it's something like they're 90 to 95% accurate locally. However, the line ratios change with redshift, and you can get individual galaxies that are over the line. And when you look with IFU data of galaxies that have star formation and age in them, you can actually look spaxel by spaxel what it looks like on that diagram, and they're kind of all over the place. They don't always sit right hugging up against that line. Sometimes you'll see half the star forming regions are over the line. And that's just, there's still age effects do that. It could be geometry effects, like I showed you. And so if you've got winds, they're going to increase those lines as well because those lines are sensitive to shock excitation. And so there are other factors when you're looking spatially resolved across galaxies. And so I would say these diagrams are only good for either nuclear or global spectra. And if you're looking at IFU data, you actually need to do a more detailed analysis. They're not so great for those.
Thank you out there, sir. Very fun.
Oh, wait, sorry. I actually have a follow-up question though, because also the stellar population models, you said like, oh, you use like an IMF as like an input, but how much would, for instance, your results change if the IMF was like not universal across like redshift?
Yeah, that's something that my former student Josh D'Agostino looked at, and so for the optical lines, it doesn't really make any difference what IMF you choose, and so we're fortunate in that way.
All right, last question.
This is actually for me rather than Chuck.
No.
There's a long-standing problem, especially in planetary nebulae, where lines formed by collision excitation and lines formed by recombination give you very different.
Yes, indeed. Yes, it's the same.
So does for instance, the fractal models help with that?
Yeah, we're looking at that now because we also see, so in addition to the recombination line, and so there's multiple offsets that we see. So there's a recombination line, and then there's an auroral line difference with the auroral lines, and then there's also a difference with the strong line methods that have been derived using the theoretical models as well. And so they're actually all three of them are producing really large discrepancies. So we're looking at that now. We haven't done that yet. That requires the larger grid of models that UFA's doing because we need to do it as a function of metallicity and as a function of ionization parameter because those lines are also, the lines that are typically used to derive these are also sensitive to ionization parameter. And we need to do it for the detailed density and temperature structures with the different types of H2 regions. So it requires a big grid, but that is part of the plan, is to see if we can help resolve those discrepancies. I personally think those discrepancies are a result of multiple different things. It's not just one. So I think geometry is certainly a factor because temperature fluctuations can cause the offset between the auroral line and the strong line methods. But it may not be just that because, for example, the planetary nebulae or the H2 regions that are selected to do these comparisons are selected in a very specific way too. And so you're actually confining the sample to specific H2 regions of specific ionization parameter ranges and metallicity ranges. If you use the full sample, you actually get some different offsets. And so there's selection effects going on as well.
With that, I think we should end, and thank Lisa again for her.